Hi, in this video we are going to discuss a duality relation between time-limited and band-limited signals. Now remember that if we start with a band-limited signal, okay, so let x of t be a band-limited signal. So x of t is a band-limited signal. That is, x of omega is equal to 0 for omega, absolute value of omega greater than omega m. So x of omega is only non-zero for frequencies omega between minus omega m and 0 outside this interval or outside this band. So now we have seen that we are able to retrieve x of t from its samples by the Shannon sampling theorem if the sampling frequency omega s is greater than 2 omega m. So we have the sampled signal xs of t, which is equal to m from minus infinity to plus infinity x of m ts delta t minus m ts. Okay, here ts is our sampling period, and in order to avoid aliasing, omega s, which is equal to 2 pi over ts, is chosen greater than 2 omega m in order to avoid aliasing. So xs of t is, now if we define p of t as the impulse train, m from minus infinity to plus infinity, delta of t minus mts. So p of t has the Fourier series representation, which is equal to k from minus infinity to plus infinity 1 over ts e to jk omega s t. Okay, and we know that xs of t is the convolution of the product of x of t and p of t. So xs of omega is, by using the modulation property, 1 over 2 pi x of omega convolved with p of omega. So this is equal to 1 over 2 pi x of omega convolved with k from minus infinity to plus infinity 1 over ts, and the Fourier transform of the complex exponential signal is 2 pi delta of omega minus k omega s So excess of omega is 2 pi's will cancel out, and we have 1 over Ts. The convolution of x of omega with delta of omega minus k omega s is x of omega minus k omega s. So the Fourier transform of excess of t is, in fact, simply a periodic repetition of the shifted replicas of x of omega. Okay, so this is the analysis for band-limited signals. Now, let us compare this analysis with the Fourier analysis, Fourier series representation of a time-limited signal. So now let x cap of t is a time-limited signal. That is, we just claim that x of t is equal to 0 for absolute value t greater than tm. Tm is a positive constant. So x of t is non-zero only in the time interval from minus tm to tm and 0 outside this interval. So note the duality between band-limited and time-limited signals from this definition. Now let us obtain a periodic extension of this time-limited signal. Obtain the periodic extension of x cap of t as follows. We call this xp, x cap of x cap sub p of t, and we are going to define this as follows: m from minus infinity to plus infinity, x of t minus m t0, where t0 is chosen to be greater than 2tm. Now here note that the role of omega s in the sampling problem is replaced by t0. We have a similar inequality. We just note that since x cap of t is time limited, if we choose the period satisfying this inequality, there will be no overlapping of the periodic extension. In the periodic extension, there will be no overlapping, which is analogous to the aliasing problem in sampling. Then, okay, x cap of cap sub p of t has the Fourier series representation k from minus infinity to plus infinity ak e to jk omega 0 t, where omega 0 is 2 pi over t0, okay, and ak will be equal to 1 over t0 from minus t0 over 2 to t0 over 2 xp of t x cap sub p of t e to minus jk omega 0 t integrated with respect to t. Now, in this interval from minus t0 over 2 to t0 over 2, x cap sub p of t will be equal to x cap of t. So in this interval, it will be equal to x cap of t. And x cap of t is time limited. Therefore, we can replace the lower limit by minus infinity and the upper limit by plus infinity. Okay, we have therefore 1 over t0 from minus infinity to plus infinity x cap of t e to minus jk omega 0 t integrated with respect to t. But this is nothing. The integral expression is just the Fourier transform of x cap of t sampled at k omega 0. So we have capital X cap of k omega 0, okay, k omega 0 divided by t0. So x cap of t will be equal to k from minus infinity to plus infinity, capital X cap of k omega 0 divided by t0 e to jk omega 0 t. Now, if we evaluate the Fourier transform, x cap of this is the periodic extension, not x cap of t, but x, the periodic extension of x cap of t. So the Fourier transform of the periodic extension will be equal to k from minus infinity to plus infinity x cap of k omega 0 divided by t0 2 pi delta of omega minus k omega 0. So if we summarize this analysis, the comparison of sampling and the Fourier series representation of the periodic extension of a time-limited signal. For the time-limited signal, we have assumed that the signal is only non-zero in the time interval from minus Tm up to Tm. Then we have obtained the periodic extension of the signal x cap of t. Here we have, of course, x cap of t minus mt0. So we have the periodic extension of x cap of t. And we have chosen the period t0 in the periodic extension, the fundamental period t0 satisfies the inequality t0 greater than 2tm. This is analogous to the inequality we have used in sampling, omega s greater than 2 omega m. Because in sampling we have a periodic function in frequency domain, and we do not want aliasing to occur. That means we do not want the shifted replicas of the Fourier transform of the band-limited signal. We do not want them to overlap. The shifted replicas must not overlap. So here we also want to avoid the overlapping of shifted replicas of the time-limited signal. Here the shift is in time, of course. So we note the dual discussions related to sampling and the periodic extension of the time-limited signal. Okay, then afterwards we obtained the Fourier series representation of the periodic extension and obtained the Fourier series in terms of the samples of the Fourier transform of the time-limited signal. And when we evaluate the Fourier transform of the Fourier series, we have now a sampling in frequency domain. So the sampling in time domain for band-limited signals is now replaced by sampling in frequency domain for the periodic extension of time-limited signals. Okay, thanks for watching.